Hi everyone. Let's wait until 8:05, then we start our week two lecture. Hey, it's time to start. And this is week two of machine learning course. And in this week, we're going to talk about the machine learning for regression and classification. And the models we're going to learn is linear model and support vector machine. That is for linear model is for the regression task, and SVM is for the classification task. And we have talked about the different machine learning tasks, like regression, classification, clustering, and so on. And we also talk about supervised learning and unsupervised learning. And this week we're going to talk about the two most popular or two most common machine learning tasks in using supervised learning, that is regression and classification task. So let's first have a look at these two tasks or problem from a geometric perspective. So the inputs in machine learning problems can also often be represented as points or vectors. So we have seen this kind of illustration in last week. Uh, let's say we can represent what, we we can represent data samples using this scatter point. And for this example, we can represent the x coordinate as sleep hours and represent the y-axis as grumpiness. And the input data should be the sleep hours, and the true label or the value we are going to expect from the model prediction would be the grumpiness. So we are expecting like to build certain kind of relationship between the input variable sleep hours and the output prediction grumpiness. So we can represent each data sample using just data point. So in this example, the input is just one-dimensional data. So that is just one feature, sleep hours, and the output is the scalar value or some kind of grumpiness score. So we are going to represent the data distribution using this scatter point plot. And similar for this one. So we can also represent the relationship between the pesticides and the tumor rates with this scatter point plot. So now we know that we can represent these data points using the points or vectors representations. Then what are we actually looking for when we are dealing with regression or classification task from a geometric view? So for regression task, that is a supervised learning problem. And the goal is to model the relationship between input X and real value output Y. And this is akin to a line or curve fitting problem. So let's look at this example again. So for regression task, we have learned that the output is real value output and it is continuous. It is not um, discrete value output. We are expecting the output are continuous real value output. So we want to establish the relationship between the input and output. We want to find some pattern or some trend between this input and output. So it is akin to fitting a line or curve based on the point distribution or the trend of this distribution. So for this example, we want to know the relationship between sleep hours and grumpiness. We can expect it that the less sleep hours we have, the more grumpiness we will be. So we can expect that there's a kind of negative relationship between the sleep hours and grumpiness, and we want to find this trend, and this trend can be represented by this straight line, and this line is our fitting result from the geometric view, and that is also what we are looking for a regression problem. So we want to find this fitting line for this regression task. And similarly, with this kind of data distribution, we cannot just use a straight line to represent the trend for this data value changes. So in this case, we are going to fit a curve to this data distribution. So it is also a regression task because uh, we want to establish the relationship between the input X and a continuous real value output Y. And it is akin to the curve fitting problem. But in contrast, for classification task, it is also a supervised learning problem. And the goal is to learn to predict which of the two or more classes an input belongs to. It is akin to learning linear or nonlinear separator for the input. So given some data points or data samples that is come already in grouped. So we have grouped colored data samples. What we are looking for in the classification task is we want to find a separator that can separate these two groups. So for this example, we want to draw a line and each group of data points will lie just on one side of the separator. And there are a few characteristics for the classification task. So that is the shape of the separator. It can be linear or non-linear. So it can be a straight line or it can be a curve. And for the expected classification categories or groups, we can have two expected groups, or we can have more than two expected groups. So if we have two expected groups, then it would be a binary classification problem. If we are expecting more than two categories, it will be multi-class classifications. So combining these two concepts, we will have like four kinds of classification tasks. So two class that is binary linear classifications. So we are expecting a straight line separator to separate the data samples into two groups. And multi-class linear classifications. So we are expecting using straight lines to separate the data samples into more than two groups. For this case, it is separating the data samples into three groups. And if the separator would be a curved line, then it is a nonlinear classification. So for this case, since the data points are from two groups, so it is binary nonlinear classifications. And for multi-class nonlinear classifications, that means we are expecting more than two groups, and we are using curved lines as the separator. So that is the linear and nonlinear classification task. So that is basically explain what we are looking for the regression and classification task from a geometric perspective. So before we start learning the actual model for these two tasks, we need to get familiar with some mathematical notation and calculations. So first, concept will be about vector and matrix. So you may have learned linear algebra.
Doctor, I
So
have a question.
yeah.
Yeah. So what kind of use cases, like when we do a machine learning, like as in practical, what are the best use cases to, to execute, to look into this for like for this particular kind of scenarios? And
Like
is there
for
any other approach also which we can take?
so as we talked about in last week, for let's say we got some information about a database of house information like
Yeah, yeah,
the
yeah.
area and
Yeah.
those kind of informations. But we want to like get a rough estimation about some like newly built house or some new house. Like we
Mhm.
maybe we are planning to buy a new house, but we want to prepare some budget for that. But we need to know like the rough amount we need to prepare so we can use regression. It is a regression task, right? We can build a machine learning model from the data samples we collected, and we can so when we input the new house information into this model, the model will give us a like guide price for the house. And for classification, maybe let's say we um let's say we are developing a drug, or we are developing a treatment plan for the using certain drugs for certain disease. We got some information about the past patients,
Mhm.
so we know like how much like what's the dosage of the drugs we use for each patient and what's the outcome of the treatment. So with this kind of data samples as the training data, we
Mhm.
can train a classification model. And
Mhm.
then a new patient come, we can input the patient information and the the dosage of the drug we are planning to deliver. And
Mhm.
then we can let the model to predict if the like the treatment outcome, like if the patient will be cured by this treatment plan on this specific patient.
Okay. Thank you. Gotcha.
Okay.
Thanks. Thanks.
Right. So for the patient treatment plan classification, so because the outcome there are only two possible outcomes, so either cured or not cured. So just two expected outcomes. So that is a binary classification problem. Just yeah. Okay.
Good. Good. Thank you.
Any other questions? Okay.
Sorry, Doctor.
Yeah.
Previous slide, classification. Could you please read it again? A supervised learning problem. Goal is to learn to predict which of the two module classes. To learn. Goal is to, what is it? Goal is to predict. Is it? The goal is to learn.
Sorry, I don't get the
Just
question. So,
that sentence doesn't make any sense either. Does it?
which sentence?
Classification,
Yeah.
a supervised learning problem, and
Yeah.
then it starts with goal is to learn to predict which of the
Oh, that should be a
two.
typo. Like learn to predict which of,
Learn to predict. Okay, good. Oh,
yeah.
thank you. Thank
Yeah.
you.
It's kind of like classify a new data point into one of the groups, right?
So the previous regression is the model, the relationship between input and output, and classification is learn to predict, is it?
Um, for regression, we want what we are going to predict is a continuous value, right? Just like
Yeah,
the house
that's right.
pricing, that they are a continuous real value. But for classification, we are expecting to predict some discrete categories, like
Yeah,
group one, group two, or something like that.
yeah,
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 it's not continuous, and those groups are not ordered. So the only meaning of this group is they are from different groups. So there's no like superior or orders within these groups.
yeah. Yeah. Thank you.
Hey, so for vector and matrix, so vector it has dimensions. So for an n-dimensional vector, it means this vector has n elements or n entries in this vector. So without explicit specifications, so the vector normally refers to a column vector. So we may sometimes also have um, a row vector. So it could be like A equals A1, A2, and AN, and so on. This is a row vector. But in convention, if without explicit specifications, so a vector normally refers to a column vector in machine learning. And the matrix is just rectangular arrangement for a bunch of um, values. So it has rows and columns. For this matrix, it has n row and d columns. So we can see that the numbering for this element, if we read it along the each column, we can see that it has n row. If we read it along the row direction, we can see that it has n elements in this row, d elements in this row. So that means it has d columns. And each row or each column of this matrix is is just a vector. Okay. Another important concept is about the vector norms and transpose. So these vector norms are normally used to define the distance. So in machine learning area, so we use distance a lot, like almost everywhere. So especially in when we define the loss function. So when we are measuring, we need this distance definitions when we want to measure the um, discrepancy between two data points. So we want to quantify like if point A is the distance between point A and B is larger than the distance between like point A and C. So we need some quantification method to represent these distance values. And also for loss function, we sometimes also need to quantify the loss um, based on some vector values. So we also need these vector norms to calculate the vector norms uh, and use these vector norms as the loss function. So we will see how we use vector norms later uh, when we talk about the actual model. But here, let's get familiar with the concept. So the first line is the general formulation for the LP norm. And this is just a general form. The most popular or the most commonly used two vector norms are the L2 norm and L1 norm. So you may have used such norms in your previous study, but it just gave it more academic names. So for L2 norm, that is the Euclidean norm. So that is measuring the Euclidean distance between two data points. And this distance can be represented as a single vector. So if we are calculating the L2 norm of a vector x, so x is a vector, and let's say x equals to x1, x2, x3. Let's say x is a vector of 3 dimensions or with 3 elements. So the L2 norm of vector x would be x1 square plus x2 square plus x3 square. And we calculate the square root of the sum. So this is just an expansion for this equation. And for L1 norm, that is calculating the sum of absolute value for each element in the vector. So the L1 norm.
Is that related to what we heard as the Manhattan distance?
Yes, that's true. That's the Manhattan distance. And that would be the absolute value of x1 plus, and this is the L1 norm, the expansion for this equation. So as the student said, the L1 norm is also called Manhattan distance, and the L2 norm is called Euclidean distance or Euclidean norm. And the last norm is the infinity norm, so it is less commonly used, but L1 norm and L2 norm is commonly used in loss function and also in some regularization terms. So especially for L2 norm, that is very common. And the transpose for a matrix is simply just flipping the x and simply flipping the row and column dimension for matrix. So we can see this example. The row before transpose become the column after transpose. So it's just flipping the row and column for the matrix. Okay. And the next is about gradient. So
Doctor, can you back to the Euclidean norm, please? can you explain again the formula? Because I miss the part.
Um,
The Euclidean, when you are under the vector norms and transposes, you have the double bracket x equal, and this is what is the number? Is 2 or 3?
uh, which one? This is the expanded form or equivalent form to
Yeah.
this
The next one
equation.
underneath, the next one
The next, you mean here? This is 1. That is this one.
is, yeah, but the next one is under norms and transpose. There is x, and then is x1 plus x2, x3. But the first one is, what is the number that you have? Because it's not clear.
This is x. You mean this one? This is x1.
No, the on left-hand side.
Left-hand side. This is 1.
It's one. Okay.
Yeah, this is the L1 norm of vector x. So it is same as
Okay, perfect.
it
Thank
is
you.
the same as this term.
Okay,
Yeah.
got it. Thank you.
Okay.
Excuse me, I've got a question as well.
Yeah.
So on those formulas, what is it that we need to know? Like to know, is it that the first formula, the general formula, or what is important for this course on that? Or we need to know all of them?
At current stage, you need to know what vector norm is calculating, and later on you will know where this norm is used when we see the actual model. So yeah, you will know it better when we actually start learning the model definition and the equations related to specific model.
Thank you.
Okay, and for gradient, the gradient is the multivariate generalization of a derivative. So for single variable function, the derivative tells you the slope. So if you have learned the derivative, let's say we have a single variable function, maybe y equals the squared value of x, and the derivative of y would be 2x, 2 times x. And this derivative is telling us the slope of the curve, right? So this should be y equals the square of x, and this derivative is telling us the slope direction, right? The slope direction for at each position on this curve. So with this gradient value or gradient function knows, we know how to optimize or how to find the smallest value for this function. So this gradient is just a multivariate generalization of this derivative concept. So it does the same thing, but in many dimensions. So we can see it from here. So instead of just calculating the derivative with respect to one variable, it is calculating derivative with each variable used in this function f. So this function f will be f x1, x2, x3, xn. Actually, this is x is a vector, so it should be like this. So instead of just calculating the derivative with respect to one variable, because we have like so many variables or so many elements defined in this vector, it is the gradient is calculating the derivative of function f with respect to each element of the vector x. And the result of this gradient is also forming a column vector. And this vector is pointing in the steepest uphill direction. So we will see how this gradient will be used when we are solving the model or finding the optimal values in the optimization process. So we will learn more about this gradient when we look at gradient descent method to optimize the model weights or model parameters. Okay. Any question till now? Okay. Let's look at the actual task we are going to do. So regression task. So regression is a method of modeling a target value based on independent predictors. So this method is mostly used for forecasting and finding out the cause and effect relationship between variables. Regression techniques mostly differ based on the number of independent variables and the type of relationship between the independent and dependent variables. So we have seen such relationship can be linear or nonlinear. So for linear relationship, it is what we are looking for is just a straight line. And for nonlinear relationship, we will fit a curve to the data points. So let's first look at a video to introduce the linear regression.
People on Depop really want your style. I'm not coming on Saturday. I'm strapped for cash.
You should sell some stuff on Depop. It's heaps easy.
I can't skip.
You can skip the ads.
Here's the button. Skip.
Press the button and skip.
Make money selling clothes you don't wear on Depop. Download now.
An important task in machine learning is prediction. Given some information summarized in an independent variable x, for example, the height of a person, predict the value of another dependent variable y, like their weight. Usually we have a training dataset. That is a table that contains values for both x and y that we want to use to infer what the function g should be. We can then use that learned function g to predict the values y for new values of x not seen in training. Finding the right function g is called regression. And the easiest way to do this is to assume that this function g is a linear function, hence the name linear regression. Here alpha is the slope of this line and beta is the intercept. The simplicity of linear regression makes it really attractive. We're only dealing with linear functions here, so no complicated neural networks involved. If you are faced with a prediction problem, linear regression should really be the first thing that you try. To do linear regression, we just need to pick the alpha and beta that makes this line fit the data as much as possible. One way to quantify the fit of a line to a bunch of data points is to consider where the point in the training dataset is and where it should be according to this line, take the square of the difference, and then take the sum over all data points. To find the alpha and beta that make this quantity as small as possible, let's take the gradient, set it to 0, and solve for alpha and beta. Congratulations, you have just solved a prediction machine learning problem from scratch. If now you want to predict the weight of a new person, you just plug their height into this formula. In practice, you don't have to do this derivation by hand. If you feel more sophisticated, you can fire up Python, import scikit-learn, declare a linear regression model, and feed it the training data, and call the fit function. To get predictions, you can just use the function predict. In addition to being simple and tractable, linear regression is also very extensible. For example, you can easily adapt linear regression to fit a model with more than just one variable as input. In the same vein, if you're not satisfied with a linear relationship, you can augment your data with nonlinear features. Another compelling aspect of linear regression is the fact that we can interpret the coefficients that we get. For example, if the slope is positive, x and y move in the same direction, and if the slope is negative, they move in opposite directions. Good luck trying to find a meaningful interpretation of the weights of a neural network. This was linear regression in 2 minutes. If you liked the video, please make sure to like and subscribe, and see you next time.
Okay. Let's look at this example of how to and explain what linear regression is doing. So let's look at this is the house price prediction example, but it is a simplified version. So in this case, we only have one feature value that should be the living area. And we have like in total 47 houses. That is the number of data samples we have. So that means we will have 47 such kind of rows in this table. And we'll have the price. That is the expected output we are going to predict. And we can plot the relationship between the living area and the price of the house. So the x coordinate would represent the living area, and the y coordinate will represent the price. And we can see the data distribution. It's like this, and we can guess that they must form such kind of linear relationship. We can use the linear regression to find the definition for this regression line. So linear regression model would be the simplest possible model in machine learning. So this is the base model for all statistical machine learning. So if we can treat x as one feature data variable, and y is the value we are trying to predict. And we can establish the relationship between x and y using this formula. Y equals to W0 plus W1 x plus epsilon. So W0 and W1 are the parameters for the regression line. So that defines the slope and the y-intercept of the regression line. So let's suppose this blue straight line is our regression line, and W1 should represent the slope of this regression line. And the W0 would be this intersection point, that is the y-intercept for this regression line. So imagine that we already got this regression line as our trained model. We already find the optimal value for this slope and y-intercept values. And we can make prediction based on this the definition or the formula for the of this regression line. So if we are given data x, so let's say if we are given a data x like here, maybe you call it let's say xi, and we can find the expected or the predicted yi value based on according to this regression line equation. So we can use this two part. So yi would be equals to w0 plus w1 xi. So we can get the prediction based on this value. And what is this epsilon? So epsilon is the unexplained or random or error component. So that measures the difference between the true data points y value with the predicted value. So it is represented by this right line, right? So for this data point, the predicted value should be this, right? This is the predicted let's say y hat. This is the predicted value with this provided x coordinate value. And the actual value for this data point is y. And this difference would be just y hat minus y. And if we just move this, and y hat is equals to w0 plus w1 and x, right? So if we just move this part to the left-hand side of the equation, we can see that this difference is just the epsilon. So it is just represents the difference between the true data point y value with the predicted y value from the model, or say from the regression line. And so if we want to achieve this, we need to find the value for W0 and W1. That means we need to know the slope and the y-intercept for this regression line. But how can we determine these two values? So we are going to do it through solving the system of equations, or we can do it through optimizing these two values using some optimization algorithms. But here, we need to first define our objectives. So here is the objectives that we want to achieve. So yi, that is the, let's say yi is the true data, true value for the data point. And W0 plus W1 plus xi, if we rewrite these terms, we can say it is equals to W0 plus W1 xi, right? And this term is the prediction from the linear model, from the linear regression model, or from the regression line, right? So if we're calculating their difference, and that would be the discrepancy of the data points away from the regression line, so represented by this right line, right? So if we square it, that will be the squared difference for each data point. And we are going to loop through all the data points from index I to from index 1 to index n. So we are calculating the squared difference for all the data points and then sum them up. So this time, this whole term would be the total squared difference, right? That would be the total squared difference. So what will be the ideal characteristic for this regression line, right? We want this. We are expecting the optimal regression line going through all these data points, right? And then in this way, we can achieve the smallest total squared difference, right? We want this regression line to go through this data point, and so that this regression line is close to all these data point and achieve small squared difference between the true data points and the corresponding prediction from the regression line. And if we sum all these difference for all the data points together, we are expecting to achieve the smallest total square difference, and this is our objective. So we want to find the W0 and W1 that can define a regression line, define a slope and intercept, so that this line can go through all the data points and achieve the smallest total square difference between the regression line and each data point.
What does the arg keyword mean, please?
Arg, it is like find the argument. It means find the argument. Find the arguments W0 and W1. So find some value for these two parameters.
Oh, thank you.
Yeah.
I'm just because I did the W, that's bias weight, isn't it? The
Yes,
weight.
it is also called bias. Yeah.
Yeah, and so why are we doing the square?
Because we are expecting some like positive values representing the difference. We want to accumulate such difference so that the total number will represent the overall difference between data points and the regression line, right? If
Yeah.
we don't use the squared, if we just, let's say, if we ignore this squared, this value can be positive, either positive or negative. Both can
Yeah.
happen, right?
Yeah.
And if we sum them up together, the total value will be like cancel out, right? The positive number and negative number will be cancel out. So we can tell the difference. Let's say this positive number and negative number will cancel out and generate a total zero difference. But for perfect line fitting, we also got zero difference. So we can't tell the difference between these two situations. So we need to use squared so that we can accumulate these positive differences and thereby differentiate this kind of two situations. Okay?
Yep. Thanks.
Sorry, doctor, here we are calculating the loss, correct? This one, the loss function.
Yes, this is the loss function. This summation term is the loss function for a linear regression model.
Yeah, and after that, we'll do optimization, like, to adjust the W0 and W1.
Yeah, the optimization is looking for the actual value of the proper value for W0 and W1 so that this loss function can be minimized.
Great, thank you.
So
Okay.
why are we not taking square root of the summed values? We are just taking the squares.
Because for mathematical computation, squared value is more, because later on we are going to calculate the gradient, right? The gradient of squared term is more convenient for calculation than like the square root. Like we can, that's one reason, and we cannot also have the square root of negative value, right? The term inside the parentheses can be negative, and we cannot calculate the square root of a negative value.
No, what I meant was that like we did in the L2 norm that we explained. So taking the squares of individual values and then summing them up and taking the square root of the sum.
we will talk about that later. But for this one, this is because that L2 norm, finally, that L2 norm use the let's go back. This L2 norm has the square root, and we will need to calculate the gradient of the loss function later, and this square root is not convenient for computation. And it is same like for optimization problem, with and without this square root will achieve the same optimization result. So if a value let's go back. If a pair of value W0 and W1 can achieve the smallest value for this function, it can also achieve the L2 norm of the same form. So that's the characteristic. So it will also both of these form will achieve the same optimal value for W0 and W1, but this form is much more convenient to calculate the gradient. Like we will see that later.
Is it because maybe to help disappearing gradients because we have a higher number on that?
Not really. We will see other type of representation. This is the vector. It is the vector form representation for the loss function. And in a few slides later, we will see the matrix form representation for the same loss function. In that case, we can represent the loss function in the L2 norm notation, but the underlying calculations are the same. We will see that later. Okay.
Yes, thank you.
Okay, let's continue. So with this loss function and our objective specified, so how can we find the W0 and W1? Straightforward way, maybe we find all the possible values for W0 and W1 and to compare for each pair of W0 and W1 values, we calculate the total square difference between the regression line and the true data points, and then we calculate the loss, and we compare which value pairs would result in the lowest loss value. And it is straightforward, but that is not smart. Because this is a simple linear regression problem, it can be solved in a closed form. So we can just use calculus to find the solution for this optimization problem. So this is rare. So only because this equation is simple, so we have the analytical solution for that. But for other more complicated models, we need the optimization method to iteratively find the optimal value for the parameter or for the weight. So anyway, let's look at the analytical solution for the linear regression model. So we have already got the let me find. We already got this loss function defined. And now we need to find the optimal value for W0 and W1. So what we are going to do with the calculus is we are going to calculate the gradient of this loss function. So we are going to this is represent the loss function. So the loss function, the gradient of loss function with respect to variable W0, and we can get this equation by setting this derivative equals to 0, and also setting the loss function, the derivative of loss function with respect to W1, and also set this equation, this derivative to 0 as well. We can solve this system of equations and get the optimal value of W0 and W1. So W0 would be the mean of all the true y values minus the W1 value multiply the mean value of all the data points x value. This is the mean of all the data points x value. And we can also get the value of W1 by following these equations. So with these analytical solutions, we can get W0 and W1's optimal value by just one calculation. So we can calculate the optimal value directly by following this equation. Okay, I think let's pause here and have a 5 minutes break, and then we continue the rest of sections in the second hour. Let's come back at 9:04.
Meanwhile, can you explain that how does this with respect to W0 comes out to be -2, and with respect to W1 it comes out to be -2xi?
Sorry, which part?
So in this derivative with respect to W0 comes
Yeah.
out to be -2 yi minus W0 y1 x1 xi, and with respect to W1 it is -2xi. Can you explain that?
That would be more about the calculus. So I can tell like briefly, but it is out of the scope of this course. There are a lot of like details, derivation for these equations. I think later on you can find more details online about those materials. But here I can say, let's say this is the loss function, right? Let's say the loss function. Let's just call it L. The loss function with respect to what is the first term? W0.
Yeah.
So we are calculating the derivative of L with respect to W0, and we can expand this summation notation. So it will become like y1 minus W0 minus W1 x1 square plus y2 and such kind of terms. So we just calculate the derivative of each terms with respect to the W0. So in this case, that would be 2y1 minus W0 W1 x1 and multiply um, there should be -1. So that would be
Got it. Yeah. Yeah.
yeah, and later the other terms are the similar. And so we can just write it back to the summation notation.
Yeah.
It will like this. And
Yeah.
similar
Got
for
it.
W1.
Yeah.
You need to use the chain rules and so on.
Yeah.
So,
Got
doctor,
it. Yeah.
here, yi, this one is true value, correct?
Sorry?
The
Yi is the true value. Yeah, the
yeah,
data point's true value.
yeah. Okay.
Hi, Dr. Zheng. I have a question. Could I ask now?
Uh, about which slides or
Um, uh, for those, because there are so many functions here, for these functions, I cannot even pronounce it correctly, like read them correctly. I just worry about in the exam, how many those functions I need to remember to go to the exam because it is a closed book exam.
you don't need to memorize those equations and also the derivations. You're not required to memorize that. But um, if you understand the underlying concept, I believe it is straightforward to you can write it out by yourself directly. Let's say um, if you are asked to write the loss function for this linear regression
Yeah,
model, it is straightforward, right? The loss
yeah.
function, you need to calculate the difference between the regression line and each point, and we want to square it and sum this difference for all the data points, and that is the loss function. And you understand this underlying concept, and writing this equation is just straight away, right? And for this kind of derivation, don't worry about that. You don't need to memorize that. It is not part of the assessment. You're not going to ask to answer what's the analytical solution for linear regression or so what. But there are some equations that is highly related to the concept. You better understand.
Okay, thank you.
Maybe here, doctor, will be utilized like Adam or SVG to calculate W0 and W1, correct?
Sorry?
Here in Python what's called will utilize Adam optimization or SVG to calculate this one, correct?
Yeah. If you use the scikit-learn library and use the linear model, it will calculate those analytical solution for you. You don't need to worry about that. Okay, let's continue. I think I would better speed up a little bit for the rest of contents. Otherwise, it will be too late for you guys. Okay. Next, if the problems become more complex, like we not only have like only one feature as the input. Let's say we have two features, living area and number of bedrooms. So in this case, we're not looking for a straight line in this 2D space. We are actually want to get regression plane in 3D spaces. We will look at that in later slides. So here is a general definition for the linear regression with higher dimensions. So we have input. We have n data samples, and each data sample comes with d features. So that means each data sample will have like x11, x12, x13, and x1d. Each input vector will have d elements in its feature vector. And the label is still because it belongs to the real value. So the label is still a single scalar value as the output, as the label. And the expected output would be the price of the house, and that would be the prediction from the model. And this is our model definitions. So we got this input vector, right? This is the vector from this input, and we are calculating the inner product between the input vector and the weight vector, because we need to have corresponding number of weight elements so that it can be multiplied with the input vector. So if the input vector has d elements, the weight vector w should also have d elements. That is representing the weight for each feature in this input vector. And we also need to have a scalar b, that is the intercept of this regression plane. So that is the general definition for a linear regression. When the dimension of input vector is more than one element. So this is an example of input vector that has two elements. So the input data sample should have two features, x1 and x2. And the true label would become the third dimension, and that would be the y. So in this case, the data points will form a 3D distributions, 3D scatter distributions in these 3D spaces, right? So now we are not, for the regression task, we are not looking for straight line or straight regression line. We are kind of looking for this blue regression plane in this case. So for input data with two dimensions, that is if input data has two features in the feature vector, we are not looking for a regression line. We are looking for this regression plane as the model. And we have no.
Excuse me, doctor. If there was x3 as well, how would you represent x3? Where would you put x3?
We cannot draw like hyperplane by hand. So it is all out of our human imagination. I
Okay.
believe so. But there's a name for the shape that is called hyperplane. So when
Yeah.
the dimension is more than 2 for regression task, if the input dimension is more than 2, like 3, 4, or even more, what we are looking for is the hyperplane. So that is a plane concept in high dimension.
Thank
Okay?
you.
And we already know how to we know the input of the linear regression model. That is the feature vector and the labels, and we know the output, that is the predicted value, and we know how to define the model so that the model can generate the prediction, and the model have a weight vector and intercept, and this W and B are the parameters we need to tune, and these parameters are controlling the shape or the performance of the regression model. How to find the optimal W and B is through the optimization. So here we use we call it least square regression. So why it is called least square? Because we are calculating the difference between prediction and the true value for the label, right? We calculate this difference and we square it. So that is the squares. And we want to find the W and B that can achieve the minimum sum for this square difference. So that is why it's called least. So that's why in total, this optimization method is called least square regression. And again, this is our loss function. And our objective is to find W and B that can achieve the minimum value for this loss function. This is our loss function.
What does T represent here?
B is the intercept.
Okay.
Okay. It is inconvenient to use this actual B as the intercept or as an actual extra weighting or extra weight or extra parameter that we need to tune for the model. It would be better to just incorporate or include this B into a single representation to represent all the parameter values we need to tune for the model. So here we can rewrite this notation in this way. So this X bar, we can append a single value 1 to the end of the previous input feature vector. And we can append the parameter B to the end of original weight vector W to form the new weight vector W bar and also form this new input feature vector. So in this way, with this representation, we can rewrite these equations using just one term. So this is our new notations to represent the prediction out of the model.
Excuse me, doctor.
Yeah.
Why in this case the X has transpose now? In previous
Because
yeah.
because X by default, that is a column vector, right? That is x1, x2, xn,
Yeah.
right? And to do this you can say vector matrix multiplication or matrix multiplication, we need to make sure the dimension is matching. So here, the W is also a column vector, right? W1,
Yeah.
2, not xn. There should be xd to WD. to do this multiplication, we need the row vector multiply the column vector, because for matrix multiplication, let's say for matrix of n row and m column, it can only multiply with another matrix that has m row, maybe let's say p columns, and the result would be a matrix of n row and p column. So the number of columns in the first term should be matching with the number of rows in the second matrix. So that's the rule. So we need to transpose this x vector into a row vector. So that will become x1 xd, right? Now it is one row d column, and this one is d row one column. So now the dimension is matching, and the result of xt of and w would be just a matrix of one row and one column. So it is just a single value, right? It is matching with our expectation. The model prediction is just a real single value, right?
Yep. Excellent. Thank you so much.
Okay.
Doctor, quick question here. So for the linear regression, we have one input feature, if I may call it, the x, and this x is a vector because it has multiple instance of it.
No. We have already made the problem more complex. So in the first example here, we have only one feature, right? So now
Yes.
x have only like it only has one feature, x1.
Okay.
And in this case, we have made it more complex. It has two features, living area and bedrooms. So now for one data sample, it should have two elements, like
two elements, and hence we need two weights
area
as well.
and bedrooms. So it has two values for each data samples, and we have many, like we have n number of x.
Yeah, that explains. That explains. I was wondering why we have multiple weights, so that explains. Thank you.
Yeah. Okay. And now for optimization, we have already rewrite our loss function, right, in the new form. So we append 1 to the input feature vector, append b to the weight vector, right? And we can rewrite this loss function. And this is the, let's say, prediction from model. This is the prediction from model. And we just write it like yi hat. And we are calculating the difference between prediction and the true value and square it and sum all the difference. And this is still our loss function. And this is the vector form. So this is the vector form representation for the loss function. And we can rewrite it to the matrix form representation. So here we need to use the summation notation in this vector form, but we want to get rid of that. So we want to use the matrix form. We also want to write all the data samples in just one matrix, right? So now we can use this X bar matrix to represent all the input information. So in this matrix, each row is a data sample. So now each row represents a feature vector for one data sample. So this row would be x11, x12, x13, x1d and 1. So this is, if we expand this x1t, t is transpose, so it is a row vector. So each row is representing one data sample in this matrix X bar. And why should be same? Is it just a column vector, and each element is just the corresponding true label for the data samples. And this is our definition for X bar and Y. Let's see how we can write the loss function in the matrix form. So if we calculate the X bar multiply the vector W bar, it is equivalent to do the multiplication for each data sample feature vector in a product with the weight vector. So this is our new matrix representation of the model prediction for all the data points. So the prediction for each data point would just one is represented by one row vector in this matrix. And then if we do the difference between this prediction matrix and the true label, we are getting the difference between prediction and true label for each data points in a single row vector in this matrix. So now each row is representing the difference between prediction and true value for each data point. Now it's time to use the L2 norm, right? So you can see that we got each element in this vector that has the difference. So if we calculate the L2 norm for this vector, that means we're going to calculate the square for each element and then sum them up. And then later on, we first calculate the L2 norm, and then we square it because we just want to get rid of the square root operations introduced by the L2 norm. So we want to get rid of this square root, so we square this L2 norm. So with this notation, this will be the matrix form of our loss function, and it is equivalent to this vector form. We can see that this is the matrix form for the linear regression loss function, and this is the vector form. So these two representation is just totally equivalent, but for the computations, so it is more efficient to calculate the matrix instead of to do this kind of like for loop to loop through all the data points and calculate this vector multiplications and so on. So it is more efficient to use the matrix form to calculate the result.
Sorry, Doctor, just a question.
Yeah.
Let's say x1. Does x1 represent, let's say we have like two parameter, area and price. Sorry, area or number of room.
Yeah.
X1 represent all the parameter in one record or all record in one parameter for one parameter.
So this x1 bar, x1 bar transpose would be say area, number of bedroom, and 1.
Yep.
Okay.
Yep. Thank you.
Okay, we have defined the task, and we know how to generate the prediction from the model because we have defined the equation for the model, and we know we need to use the least square regression to form the loss function, and now it's time to find the optimal value for these weight vectors. So we have seen how to use the analytical solutions to find the values for W. And we will also learn how to use the gradient descent method to find the optimal values. So this is just an analytical solution, but in different form. So we have already seen the analytical solutions for one-dimensional case, right? The input data only have one feature in the input vector. For higher dimension input vector, and this is the analytical solutions for that. So I will just you can find more detailed derivation for these equations, but here we can get the analytical solution directly following this equation. And we can get the analytical, we can get the optimal value for W bar directly from this equation. But for other more complicated data, analytical solution normally not available at all. So in that case, we need to use the gradient descent, such kind of optimization method to iteratively find the optimal value for W. So the purpose of this optimization or the mechanism of this optimization method is it start from certain value for these weighting parameters, and then it slightly change the value for these parameters to see how the loss function changed. And with such information known, the algorithm would know how to tune each parameter so that the total loss would keep decreasing iteratively. So let's look at this, the basic method from this optimization, that is the gradient descent method. So we got this objective function defined, that is our loss function. So that is the difference between prediction and true value for each data sample. We square it, we get the square difference, and we sum them up. That is the total difference. And lastly, we divide it by n so that we don't get very large loss value. Because if we have like millions or even billions of data points, this sum of square difference will generate very large numbers, and it is not necessary to keep those large values. So we can just divide this total value by n. So now the loss function would represent kind of average loss instead of total loss. The purpose of optimization is to find the value for vector W so that the value of loss function can be minimized. The procedure of gradient descent algorithm will be listed here. So it first randomly initialize with the W0. So this is the W value at iteration 0. So that we can have some like starting point for comparison later. So for like we are going to do such kind of update of the weighting parameters iteratively. So in each iteration, we first calculating the gradient at WT. So that is the gradient of loss function with respect to the weight vector. So this gradient will tell the algorithm how to tune each weight parameter to decrease the value of loss function, because the gradient of this loss function is actually telling like how to change each weighting variables, so that the total loss value will be decreased. And here is the update method for inside each iterations. So we got the gradient at WT, and then we tune this parameter, this weight parameter values along the negative direction of the gradient. So the gradient is telling us like how to tune the parameters to make the function increase, but we want the loss function to decrease, so we need to go along the negative direction of the gradient. So that is the opposite direction of the gradient shows. So we do it like WT, that is the weight parameter values at iteration t minus alpha and gradient at iteration t. So this alpha is called step size or learning rate. So it is controlling how fast we update the weight parameters, or how much values we want to update the weight values. And the result will be assigned as the weight values in next iterations. And this process will be repeated again and again, so that finally it can find the optimal weight parameter values that cannot like further decrease the loss function. So this is the visual representation for this process. So we may start from like here. It is just the initialization of W0. And this xy, it is not the input vector xy. It is representing like it is representing the weight parameters. So x is representing one weight parameters, and y is another weight parameters. You can treat it like W0, and this is W1. You can treat it like W0. So this W0 is not same as this W0. This W0 is representing the W value at iteration 0. Here, this W0 and W1 is just representing the two elements in the weight vector, W0 and W1. So this gradient is telling us which direction will make the loss function going up, right? So this Z will be the loss function in this context. So our goal is to achieve the minimum loss. So we need to go along the opposite direction of the gradient. So we update the value for W1 and W0 in each iteration, so that maybe in next iteration, we are moving downside towards the lowest point. And then we calculate the gradient again. Now it's showing that this direction is the uphill direction. So we further update the parameter values to this point, and we calculate the gradient again, and we keep this iterative updates again and again. And finally, we will reach to this lowest point that would generate the lowest loss value. And the x and y coordinate, or the W1 and W0 value at this point would be the optimal value for the weight vector that can achieve lowest loss value. So this is just a visual representation for this gradient descent algorithm process. And there are other variants for the gradient descent, like stochastic gradient descent and stochastic gradient descent with momentum, and other like RMS-Prof and ADAM. And we will talk about more about stochastic gradient descent in week 4 or 5 later. And for the other variants, if you are interested, feel free to find some materials to know more about it. Okay, and here is some summary for the optimization for the linear regression model. So here, this is the analytical solution for that, and to get the optimal value for the weight vector, and this is the procedure of using gradient descent method to achieve the optimal values for W vector. And here are some real-world example of linear regression model applications. So it can be used as forecasting sales, cash forecasting, analyzing survey data, stock prediction, predicting consumer behavior, analysis of relationship between variables. Here's another video talking about using linear regression models to predict the stock price. So the address is here, so I will save the time for you to view it after the class. And this part will be about polynomial regression and overfitting, underfitting problems, and cross-validation and hyperparameter tuning and so on. And this section would be more related to our lab work. I will leave this part to Friday sessions. So at the start of Friday lab sessions, I will talk about this cross-validation, overfitting, underfitting problems, and also polynomial regression. But for now, I will keep talking about the classification model and SVM. So is there any questions till now? Good? Okay. So let's look at the classification problem. So especially for binary classifications. So here, for binary classifications, we are expecting to use model to classify the input into two possible outcomes, either positive prediction or negative prediction. So we have two possible outcomes for binary classifications. So we have seen the application of using this binary classification model to do the spam email detection. So the email would be classified as either spam email or not spam email. So from a geometric perspective, doing the binary classification is akin to find separator between the different groups of data points, right? So this straight line separator is what we are looking for a linear binary classification. And similar for this one, we got data points comes in two groups, either yellow group or blue group, and we want to find a straight line that can separate these two groups of data points so that each group will reside only on one side of this separator. And these two cases are all about 2D cases, right? The data points all come with two feature values. So one is represented by x coordinate values, and another one is represented by y coordinate values. So for such kind of 2D cases, classification problems, so the separator we are looking for is either straight line or maybe we are looking for a curved line. If the problems goes more complex, like if the data points is 3D, if the data points are distributed in 3D spaces instead of the 2D space, what we are looking for is separating plane. So we are not looking for a separate line anymore. So for higher spaces, we are looking for separating a plane. And for even more higher dimensions, like more than 3D dimensions, the separator will be hyperplane. So just like the regression problems. So for high dimension data problems, we are looking for hyperplane as the model. And before we get into the actual model, support vector machine, we need to define the distance. So what is the distance between a data point and a hyperplane? So we got a data point Z, and we got a hyperplane that should be, let's say, it is H. And this is the definition for the hyperplane. So it is the general form to represent a hyperplane. And how can we define the distance between this point Z to this hyperplane H? This distance would be the minimum distance between data point Z, and all the possible candidate X on hyperplane H. So we may have like many distance from Z to the point on hyperplane H, but only the smallest distance among this distance will define the distance between data point Z to hyperplane H. So that is the definition for the distance between point and hyperplane, and it is also called the projection. Project a point onto a hyperplane. So this projection location on this hyperplane can be derived using this formula. So W is this W, and B is this B in the definition of hyperplane. And Z, that is the location of the data points. And all the others, W, are also the weight vector of this hyperplane. So this W and B are used to define the location and the angles of this hyperplane. And this projection, location X, can be derived from this equations. So I'm not going to go through the derivation. And the distance, this is L2. The L2 distance, or the Euclidean distance between Z and the hyperplane H, can be calculated using this equation. And the detailed derivation can be found here. I will just leave it to you. But here you just know the concept of distance between a point and a hyperplane. And you know that we can get this distance following this equation. So support, next we're going to talk about the support vector machine, and this is a widely used machine. And before deep learning, this SVM is normally used as like benchmarking models, and it dominates this field of classifications and also regressions. So although it is a classification model, but this model can be used for both classification and regression. And you can see that in the lab notebook and exercise. So SVM is a very strong off-the-shelf supervised learning technique. It was first introduced in 1963, and later on, there are many variants developed based on this version, and the kernel variants was proposed in 1992. And let's see what we are expecting out of the SVM model. So we're working on a classification task, and let's say we are provided by these two groups of data points. One group is colored in blue and one in red. And we are looking for a straight line separator to separate these two data points into two groups, and this separator will be our classification model. But how do we find what is the optimal location for this separator? So with the given only these data samples or data points, we can draw many candidate separators. Like we can draw the separator like this. We can draw the separator like this. Like all these candidates can perfectly separate the data points into two groups with no classification error, right? But which one is optimal? Which one is our preferred candidates? So for SVM model, so it would the SVM model will position this separator so that the distance between the separator and the other data points will be as wide as possible. So the distance between it is expecting this separator has wide distance to either side of the data points. So intuitively, so we want a separator that is placed right in the middle between these two groups of data points. And here it comes a definition of term called margin. So the SVM want to propose a hyperplane that maximizes the margin. The margin here is defined in here. So we already know the definition between any data points to the hyperplane, right? So if we can calculate this distance for all the data points, and there must be a smallest value for all this distance. And the margin is defined as the smallest distance among all these data points to hyperplane distance. And here is the definition for the margin. We already saw this distance definitions in this slide. So these equations are just identical. But for margin is the smallest distance from all the data points to hyperplane distance. So we may have many distance. We have distance from all the data points to this hyperplane. But which one would define the margin? That would be this one, right? This distance is the smallest distance among all these data point to hyperplane distance. Okay. And now we want to maximize this margin, the support vector machine. So the ideal separator will have this margin maximized. So the maximization for this margin will place this separator right in the middle between the two groups. So now it becomes the optimization problem, right? So we are going to maximizing the margin. So here is the definition or the equation for calculating the margin. And again, we just append 1 to the input vector and append parameter b to the weight vector w. So we can rewrite this form. We can rewrite this form to this one. So we can get rid of the plus b and turn this equations into just one term.
Excuse me, doctor.
Yeah.
Why we want to maximize the margin? Is the margin is the distance?
Yeah, the margin is the smallest distance. So we first calculate all the distance between all the data points to the hyperplane, and only the smallest distance defines the margin. So let's say we can have a separator like this. Now, what is the margin? The margin must be defined by this red point or this blue point, right?
Yep.
But this position of the hyperplane is not ideal. At least from our intuition, it's not ideal. We are expecting this separator. It would be best to place this separator right in the middle between these two data points, right? Maybe there is another let's say red data point located here, but this red separator would just classify this data point as a blue point because it is on the same side as the blue data points. But actually, this new data point is very close to this red data points, and it will make this separator not that reliable on unseen data or the new data. So we want to maximize this margin so that this hyperplane's position would be optimal, and it will be more stable to predict or classify the future unseen data. Does it make sense?
Okay. Yeah. I thought that the smallest distance would be minimized.
Yeah, smallest distance. With the distance is with this that's given this hyperplane is fixed. We first find the smallest distance, and that is the margin. And we want to maximize the smallest distance. It's kind of like this data point is pushing this hyperplane away from it. Like both sides of this this data point is pushing this hyperplane away from it.
Okay.
And then at some stage, their strength is they have equal strength at both sides, and the hyperplane cannot move anymore. It's kind of that feeling. So we want to maximize this smallest distance.
Yep. I got it. Thank you so much.
Yeah. Okay.
Doctor, sorry. In the previous slide, how do we drop the b from that the last equation?
So here we just append 1 to the xj and append w to b. So this is the vector inner product. So it is element by element multiplication and sum the multiplication together. So
right. Okay, gotcha.
Yeah, we saw it
Thank you.
in the regression example. Okay, and now it is an optimization problem. So we want to, this is the margin, and we want to maximize the margin. So that means we want to find the value for W vector so that the minimum distance can be maximized. So this will be some derivation for this loss function. So here we our objective function. So we want this minimum distance to be maximized, and it is equivalent. It can be rewritten in this way. So we can put, because the denominator is irrelevant to this j, so we can put this the minimum distance to the numerator of this equation. And we can introduce a constraint saying this term is equals to 1. It's kind of like assumption, or it is constrained. So we constrain this term as 1, and so that the numerator will be simplified as just 1. And then minimizing this 1 divided by the L2 norm of W would be equivalent to finding the minimum value for the squared L2 norm. So find the maximum value for this would be equivalent to find the minimum value for this form. So it is just a conversion, mass conversion, and we still keep the same constraint, and then we can rewrite this constraint as this. So the minimum distance is equals to 1. So that means the other data point must have greater distance than this minimum distance. So that means this term must have distance greater or equals to 1. At least it should have like distance 1. So it just rewrite this constraint in this way. And this is our loss function or our objectives. So we want to find a vector W that can achieve minimum value for this function. And this form is equivalent form for the SVM. So if we just put the data point coordinates into this into this equation, we can get the classification result out of it. So that's why I said it is equivalent form of SVM. So, and this form is called hard SVM. Let me. So it is called hard SVM. So that means the data must be separable. It cannot tolerate any misclassification. It cannot tolerate any errors. Like for example, what if the data is inseparable? So what does it mean is we cannot find a straight line that will like perfectly separate the data points into their own groups. So we can always have misclassification in this case. So then in this situation, the data is inseparable. And so how can we deal with this kind of situations? So we cannot use hard SVM anymore because the harder SVM doesn't accept any tolerance. So it cannot accept any misclassifications. So if we feed this data into the SVM model, it will generate no result. It will pop up errors. And we can, for SVM, for the basic SVM version, it is a linear separator. It will looking for a linear separator. That means it will only looking for a straight line or plane. It cannot use a curve to separate this data point. It cannot just look for this kind of curve separator to perfectly separate the data point. So if the data distribution is like this, we cannot use hard SVM to do the classification task. Then how can we deal with this kind of situation? So we will use the soft SVM. So the above version is hard SVM, and the version in below is the soft SVM. So we have seen this before, but in previous version, this term is on the right-hand side. So it just move it to the left-hand side. So it add a relaxation term to this condition and also introduce this penalty term in the loss function for soft SVM. So what does it mean is with these relaxation terms, the model now can accept certain level of tolerance. So let's say if this Xij is less than 0 or equal to 0, that means this term must be less than or equals to 0. So in this case, it will be same as the hard SVM, right? So when Zij is less than or equals to 0, that means now the soft SVM is just the hard SVM. So there is no penalty introduced because if Xij is less than 0, this Zij plus will use the maximum value between Zij and 0, and it must be 0. So 0 is replacing these terms, and it will just be a hard SVM version. So what if the Zij is greater than 0? That means the constraint is violated, and it means the data is inseparable. So in that case, Zij is greater than 0, and the maximum between Zj and 0 will be Zj. So this Zj plus will be Zj, and it will introduce these penalty terms to these violated data points. So what it means is when the algorithm or when the SVM is looking for the optimal value for W, it not only want to find a hyperplane that can separate the data points, it also want to maintain a very low level of penalized value. So where this penalization come from is these are the data points that is inseparable or misclassified. So it want to maintain low level of misclassified data. So if certain data is misclassified, it would be better to just to place those data close to the hyperplane instead of place it on the very far side of the wrong side of the hyperplane. So the intuition for this violation term would be telling this kind of intuition. So with this relaxation term introduced, now the soft SVM model can have tolerance. It can tolerate certain level of misclassified data. So that means in soft SVM, there are a few data points that can be placed on the wrong side of the hyperplane. Here is just a equivalent form for the soft SVM. We have seen this definition in previous slides. This is the soft SVM. So if we just replace the Zj with this equation, we can just get rid of the Zj and rewrite the loss function. So it is just a rewritten version for the soft SVM. So we have seen how to deal with inseparable classification data. What if the data distribution is like this? Like there are blue groups distributed surrounding the red groups. So in this case, using SVM model will not we cannot find a straight line that can perfectly separate both groups, right? So we cannot draw a line that makes no classification errors. Even with soft SVM, the classification error is very high because there's still fair amount of data, let's say blue data points that is classified as the red group if we are only using the straight line as the separator. But how can we deal with this kind of situations? So there is a technique called kernel tricks. So also called kernel SVM. So with a kernel function introduced, we can project or we can introduce an extra dimension to the data point because since we cannot it is not separable in 2D space. What if we are introduced in the third dimension? So in this case, it is I believe it is using some kind of polynomial kernel. So it introduced the third dimension so that now all these data points are scattered in the 3D spaces. And in this case, we can see that for this 2D inseparable data, now it is separable in 3D spaces. And we can find this cutting plane or this plane as the separator to separate these both groups of data. So I will just leave this kernel SVM to you to explore in after the lecture. So the purpose for this kernel method or kernel SVM is to do the nonlinear classification. So it is not using straight line or plane as the separator anymore. It is introducing nonlinearity to the separator. And not only for for regression, the SVM can also be used for SVM not only can also be used for regression. It is not only used for classification. So if you have previewed the lab notebooks, so you may have seen that we are using SVC from the scikit-learn model. That is the SVM for classification model to do the classification task. And we are using the SVR, that is the SVM model for regression task. So support vector regression, or also called SVR. So instead of maximizing a margin between the two groups of data points, this regression model tries to fit the data within a cube of width epsilon. And the idea is that the points inside this tube will not contribute to the error. Only those data points reside outside the tube will contribute to the error. So that means those data points outside the tube will contribute to shape and locate the location of the regression line. So that is how the SVR it works. So it utilizes this select variable. So those data points sit outside the tube would be called the select variable. So those select variables will help to shape the position and the angle of the regression line from SVR. Okay, and here is some equations related to SVR. We can see some similar terms like the squared of L2 norm of weight vector, and we can see this is the penalty term. It is penalizing the data points or the select variable sit outside the tube, and this term will be used to shape the regression line from SVR. And here some constraint. So we can see some similar constraint, like this would be the distance between the select variable and the boundary of the tube. So it is setting some constraint or the difference between the select variable and the tube boundary. Say this epsilon is defining the width of the tube, and this psi I again it is affecting the tolerance level for that. And this C is a coefficient to control the strictness of the regression fit. So if you set a very large number, so the regression line will be like more affected by the like noise or some outlier data. If you set this Z as very low level, and the model will be more prone to be underfitting. So C is a hyperparameter to controlling the contribution of the periodic term. You will have a chance to play with such kind of hyperparameters in the lab practice. Okay, here are some common SVM applications especially for classification, like face detection, text and hypertext categorization, classification of images, bioinformatics, and others applications. So all of them related to like classification task. And here's another video talking about the support vector machine. I will just leave it to you. Let's just finish the last few quiz questions so that to solid our understanding about the concept. So what is called the average square difference between classifier predicted output and actual output?
B.
Yes, that's mean squared error. And for next one, suppose you are using a linear SVM classifier with two-class classification problem. Now you have been given the following data in which some points are circled red that represent support vectors. For the concept of support vectors, I forgot to mention that for SVM, so what support vector means? That is the data points that defines the margin. So those data points are the support vectors. It is like those data points are pushing the hyperplane so that these hyperplane are in stable condition. So these hyperplane are supported by this data points. So that's why these data points are called support vectors. So the support vectors are the data points that sit on the boundary of the hyperplane margin. So those data points sit on the margin would be the supporting vector of SVM. So come back to this question. So if you remove the following any one red point from the data, will the decision boundary change? So currently, I believe for SVM, the decision boundary would be like this, right? So it kind of like sit in the middle between these two groups. So what if we remove this data from the input? Will the hyperplane or separator change?
Yes.
Yes, that's true. And what if we keep this one but remove this one?
Yes.
Yeah, that's correct. What about we only remove the last one?
It would stay the same, but it would get wider.
I believe it should be rotated like this, right? Because if we remove this one, but keep these two.
Oh, keep the other two. Okay.
Yeah. Yeah, and now this data point will become the new support vector, right? Okay, so for this one it should be B, and this one should be A. So the decision boundary would be changed. So if you remove the non-red circle points from the data, the decision boundary will change. That's false because the hyperplane or the separator are not defined by those
Only by SVM.
non-supporting vectors. So the positions are only determined by supporting vectors. So it doesn't matter if we remove any other non-supporting vector data points. So this one would be false. So I'm using all features of my dataset and achieve 100%. Okay, so I will leave this question to Friday lab session because it is about overfitting and underfitting. Okay, sorry about the delay, but we have pretty much a lot of contents to deliver. Is there any question for today's content?
Doctor, just for the equation, as there is a number of equation here, are we responsible on this one to memorize during the exam, or it will be I'll be using, like, let's say, Python built-in function instead for calculation?
You mean final exam, right?
Yeah.
Final exam will not test your coding, so it will not test your familiarity with Python or TensorFlow framework or scikit-learn framework. It doesn't have coding questions. It won't ask you that kind of question.
And even the question for calculation, correct? For this, to use this equation.
It is possible to have some calculations, but very simple. It can be done even without calculator. And regarding the form of final exam, I'm not sure. I haven't received the final confirmation of if it is closed book or open book. I'm still waiting for the university's decision. But the formal notification. But from previous years, it is closed book. But I'm still waiting for the final confirmation from the university. Any other question?
Yes, I have a quick one.
Yeah.
How do you select which points to be the support vector points?
It's
How
not.
do you know which ones
It's
should
not determined by us manually. So it is determined by the optimization process. So let's go back to the basic version. So for not this one. So for support vector machine, our objective is to maximize the margin, right? So this is our objective. We want to maximize the margin, and to achieve these objectives, we can, after achieving this objective, we can get the W set, right? We can get this W vectors set because we are doing this kind of optimization. We are doing this kind of optimization. We are looking for vector W that can achieve minimum value for this equation. So that means we can get we can find a W. We can find a W. That W would be the W and B because that is W bar. So we can find this W bar that will incorporate both original W vector and B intercept. So with this W determined, this hyperplane location is determined, and this margin will be defined by the hyperplane to its closest data point. And the closest data point, we call it supporting vector. We're not doing the other way around. We are not find the supporting vectors, then determine the separator. We're kind of doing the like reverse order. We find the hyperator and we give the data points that is closest to the hyperplane a name called supporting vector.
Okay, with you. Thank you.
Doctor, I have got two questions.
Yeah.
The first one is regarding the Xi star. What's the difference with Xi star and Xi?
You mean SVR?
Yeah,
Yeah.
this one. This
Yeah.
constraint.
For those select variables that is above the tube, that would be Xi. That would be the Xi. And those select variables that is below the tube is Xi Xi star, because you can see the order. It is using the data point value minus the prediction, and this is using the prediction minus the data point values. So the purpose is it want to keep this value on the left hand side to be positive, because if we are like using this y minus the location of this boundary, we will get negative values. So we want to keep this difference to be positive values in this constraint. So we just change the order to make it using the boundary minus the y coordinate of the select variable. And we then denote the tolerance to be Xi star.
Okay, so with each xi, I mean, for example, x1, 2, 3, xi would just have a one xi, or are we going to have both xi and Xi star?
It only have one. Like it only have one. If it is above the tube, it only have the Xi. If the select variable is below the tube, that it only has the Xi star.
Yep. Got it. Another question is a very general question. Why we introduced the p-norm vector function?
Here when we talk about
That's the very beginning of the lecture.
when we talk about the matrix form of recall that the matrix form for this linear regression model. So the loss function of linear regression model have like vector form and matrix form, right? So this is the vector form of the loss function, and this is the matrix form of the loss function. They are representing the like same function, but just representing with different notation. One is based on the vector, and one is based on the matrix. And this matrix form is using the L2 norm of the vector, right? So it is you can see this is the L2 norm. So with this notation introduced at the beginning, you know that this notation is actually calculating the squared of each. This is squared. This is squared. The squared of each vector element, and then plus them together. So this is the squared, and this is the sum, right? So it explains why this matrix form is equivalent to this vector form.
Okay. Yep, got it. Thank you so much.
Okay. Okay, all good?
Yep.
Yeah, great. Thanks for coming, and thanks for staying so late. I will see you on Friday live sessions.
Thank
you.
Thank you. Have a good
Take
evening.
care.
Bye.
Bye.
you.
Thanks, everyone.